All right, then thanks for the introduction and welcome all in California to my talk from dark and gray Germany here, almost evening. Yeah, I want to talk today about joint work with a student, Sebastian Hoffmann, and on representation learning and custom loss functions for atmospheric data. And I also want to, at the end of my talk, give a little bit of an outlook or pose some open questions that maybe might be a little bit of a transition to our workshop in the next weeks. Good. So what is the problem we started from? And the question is really machine learning relies on good and informative, effective loss functions. And that this is actually an issue we can see here. This is vorticity from ERA 5 reanalysis. And we will look at the MSE or L2 loss function. That's the standard loss most people, at least will start with in machine learning, as a function of time. So we evolve now in time forward, and we look at the distance we get between the reference time and the new signal. And you see in the figure that there's this continuous motion, and so far also the arrow actually goes up. But if you go a little bit further, after about 35 hours, you see that the loss or the error actually plateaus, and the MSE or L2 function doesn't give us any more information. Although if you look at the picture, we clearly see that there's still the imprints of the starting configuration are still there. For example, right in the center, there's this big arc. This was already there at the beginning. But after 30 hours, our loss function doesn't give us any more information, which would be fine for very fine scales, but for very coarse scales, we have a much longer decorrelation time than what we see here. So, and that's a well-known fact that the standard mathematical norms are not always particularly effective for machine learning and for training neural networks. And our starting point was in some sense that similar issue exists for natural images. And this is also a little bit where my background is actually in. And here's one example. This is super resolution. So you take a coarse image, like a few hundred pixels times a few hundred pixels, and you try to add or hallucinate detail into the image. And maybe it's best to look at the left, the inset of the eye. Where you see the super resolution worked, there's no obvious artifact, but if you compare it to the high resolution image, you see that there's a lot of detail missing, especially right under the eye. All these fine details are missing. If you use, and the left image, this was generated with an MSE error or MSE loss function, this generates these overly smooth details. And if you use a more sophisticated loss function, actually, like this one and especially this one, you see a lot of these details right under the eye actually can appear in the super resolution if you use a better and more sophisticated loss function. And what is this idea of this loss function? The starting point is to look at how does a neural network actually work, or what you see here, these are the layers of a neural network trained on for image classification. And you see at the input layer, very close to the input, you have very basic features, geometric features, edge detectors, circle detectors, things like this. But if you go further down in the network, then actually what is represented by the neurons in the network are actually more complex structures. Here we already see in the center left, you see tires, car tires, and at the bottom we already see a sitting person. And if you go further down, we see that you really have kind of cats and dogs and humans. And these are really present in some sense in the neural network. And the idea that was used for the super resolution was to use, and that's not only in this work, but it's a general idea, to use really the internal representation of a neural network, this feature space that is generated through the learning of a network. And the key point is that this is really a domain-specific feature space. So because we train the neural network to do image classification and maybe on specific set of images, this feature space really is tuned to this application. And the idea is then, well, why don't we actually use this specific space where the data is transformed to in this nonlinear fashion through a neural network as our space where we actually compute the distance measure. So, and this is really how you get these two images in the center here, where you have the detail under the eye and in general the detail in the super resolution. And here that's the second example where you have do neural style transfer. So you take the image on the top left and you try to paint it with a neural network in a, for example, like a Van Gogh painting or an expressionistic style. And here you also see that you kind of want to preserve a core scale structure that is present in some of the layers of a neural network, but you want to modify maybe some of the earlier layer features. Good. So one important realization that also was made in this context is that it actually doesn't really matter on what we train our neural network, as long as it's some domain relevant task. Like what I showed before, this network was trained on image classification, but if you actually train the network on anything that has to understand in a certain sense the structure of natural images in this example, then this is actually enough to get these useful internal feature representations in the deeper layers of the neural network. And why is this useful or important? Well, here's one example where this is called a pretext task. If you train a neural network with a task that is not really related to your final application. Here, what was done here is you took an image, you cropped out a region, for example, the square in the center, and then you trained the neural network to fill in the part that was deleted. And the crucial difference to the classification we saw before is that you do no longer need label data. And that's clearly a big advantage because, yeah, labeling all of these images is a very tedious task. And if we can avoid it, it saves us work and also allows us to have much larger training data sets. And that's actually really important. For example, for very large neural networks that are today trained for natural images with billions of parameters literally, there are just no data sets that are big enough. So you always do some training on unlabeled data with some task that was, you came up with where the network doesn't have to actually have labels. And here's a second example. So here the input is the color image on the left, the oranges, and you just delete the color information and then here both the color information and actually also the grayscale information. You ask a neural network to predict the information you deleted. So previously we saw it with the image region, and here it's actually with the color information. So, and that's again, you don't need labeled data. You can easily generate it from any images you have, and the network is still forced to understand some semantics of the data. For example, if you go previously, here the neural network has to understand, oh, that's a cityscape scene, and it has to continuous straight edges and all these things to do a reasonable job on this fill-in or in-painting task. Good. So this was essentially the starting point, and then we thought, well, how can we take these ideas and transfer them to atmospheric data? And what we mean by atmospheric data? Well, we were interested in wind fields, vorticity, divergence, temperature, things like this. And the analogy to the images came really because if you look at the grid representations, we are really image-like. So we have a usual disadvantages, for example, the distortions at the poles you get in the grid representation, but it was a good starting point. And the first thing we actually tried was to use the networks that are trained on natural images and see if they worked, but they didn't work. So that's how this work actually came together. And yeah, another point about atmospheric data is that ERA5 provides us with a well-curated data set from my point of view, and it contains also a lot of effects we cannot model in the simulation. So that's a little bit also my background. Yeah, ERA5 contains all the things we cannot have in our simulations at the moment. Yeah, and the big issue but with ERA5 is it's an unlabeled data set. So this is why we need something like this in-painting task we saw before also for our application. So, and the core part of the talk is this work on how we actually learned and constructed a custom distance function or distance metric for vorticity and divergence. And we used these two fields because they together represent the wind velocity vector field, or the potentials, if you want, of a wind velocity vector field. So, and that's kind of the most important dynamic variable in atmospheric dynamics. And the second reason, or the second part, what we did is we used our distance metric to validate it on GAN-based super resolution. That's essentially what we saw before with the eye example, but we wanted to do super resolution on atmospheric data. And this was recently also done by Stengel et al. And so we had readily available baseline we could compare against. If actually this custom distance metric improves performance in practice. Good. So the key question is clearly, what is our pretext task? So what do we use instead of inpainting? And for me, a key point is we wanted to use something that contains this time evolution. So natural images with aesthetic images, and we could have used actually with inpainting, something like the inpainting task. But I think this time evolution is something that is really critical. So, and something we really wanted to use. And so what we started off with was this idea. We have a sequence of fields, for example, vorticity fields. And here I said from 1979 to 2020, because we worked with this reanalysis data, but it could easily also be simulation data. You have a time step. At every time step, you get out some state of your, for example, vorticity and divergence, or your wind velocity vector field, and so on. So there was no strict assumption of what the sequence is. We just said we have a sequence, a temporal sequence of these spatial fields. And clearly, we can now look at two different fields where there's some epsilon apart or some delta t apart. And here you see we evolved a little bit with flow, but we're still close by. And what we now did, the task we designed, is we feed these two images to a neural network. We will talk about the details of this network in a bit. And that's the key part of our work, this representation network. From this, we want to derive then our distance metric. So that's really the most interesting part. But to train this network, we needed a little bit more. We added a classification network, just a small network that takes the output of a representation network and predicts the time difference. We know as input, we know the time difference because we picked two slices from this data set. But now we ask the network, given these two images, and I showed before that, yeah, you see there's kind of the flow evolved a little bit. And the network is now asked to look at this difference, how the vorticity in this case evolved over time, and to predict us the time difference. And that's what is visualized at the top. We get some probabilities for different delta t's that are available with different classes. And yeah, this is essentially our pretext task, which inherently involves essentially this dynamic character of atmospheric dynamics. And that's really the tricky, the most complicated part there, how these different scales and everything interacts. So yeah, and from this representation network, we then get this feature space shown on the, or visualized on the top left. And then we really use this again to measure our distance function. And that's essentially, in a nutshell, what we did. But I want to talk a little bit more about the details. And yeah, so we then take the activations, the HJ of a neural network in the last layer in our example, and just take the norm of these, and this gives us the distance measure that is really tuned to our application or to atmospheric dynamics in this sense. Good. How we implemented this, our starting point was ERFI pre-analysis, and we took 1979 to 2006. And as I said, vorticity and divergence, because it's the wind velocity vector field. It's actually, the distribution is not very Gaussian, so we had to do we had to log transform this data to train it. And yeah, we started with a full resolution grid data, which is 1028 times 256, which is very large, and we sampled it into smaller patches, so just so that we can train it more easily and train it at all in finite time. And for the beginning, we just used one vertical layer. And yeah, what we did with each of these two slices, whether these delta t apart, we fed them to our representation network. So that's this network you saw before, here in more detail. And that's a fairly standard network architecture from computer vision. So you have these residual blocks, very standard. What is not standard, was a bit peculiar about this architecture, is that you have these two identical blocks. You see, they're topologically identical. We are not only topologically identical, we share the same weight. So you really have two copies of the same network, and you feed the two input signals, the T and delta T, through the same neural network. You get an output, and then you take this output and feed it to the classification network. So in machine learning, this is called a Siamese network. I would say you have one network and you put in through signals, but yeah, in machine learning, it's considered you have the Siamese network with 2 copies of the same network that share the weight. And yeah, our representation network, maybe one thing that is noteworthy, it's actually a very tiny network for modern standards. So it has 2.27 million parameters. As I said before, in computer vision networks with billions of parameters are trained today. But you will see the reason why it's actually rather small still in a minute. And yeah, that's the representation network. So it's a standard convolutional network with, in our case, yeah, really 4 layers. And that's what we use. And the hope is that this violet layer then contains useful information we can use to derive or use as a distance metric for this atmospheric data. The training used the delta T at most 69 hours. We experimented with different times, but 3 to 4 days was the most that actually worked for us. We used a little bit of pre-training with a subset of the data to improve convergence, and that's the training graph we got. So it looks pretty standard. Blue, the training data goes down. Eventually, the test data or the evaluation set goes up again. What you see here is that the evaluation set goes up actually pretty early, and that's also the reason why we used a fairly small network, because yeah, we quickly got to overfitting, and increasing the network size only made this problem worse. So I think that's one thing where one could still improve things in the future to maybe improve a training procedure, use more data, something along these lines. Good. And yeah, so that is essentially the idea. We have the network I showed. We train it on all these different delta T slices from a real analysis data set, and have a network predict the time difference, and hope that to predict the time difference in the network, it actually has to come up with a useful internal representation we can also use for different tasks. And to see if this works, we really looked at the super resolution. I will get to in a minute, but we also looked at more intrinsic evaluation. And this was, if we have these 2 fields, we can compute actually the MSE error. That's what we already saw at the very beginning. But we also can compute our new, what is often called a content loss. I have here the subscript AD for ATMO_dist. And just to recall, this ATMO_distance is we take the last layers of a neural network, and from these, then we just take the activations of a network and compute the standard mathematical L2 norm in our case, or the squared 2 norm, and this is then the distance measure. And now we plot this actually as a function of delta T. So this is what you see here. We average over all different time slices we have in our data, and we look at how big is actually the error or the loss we get. And what you see here is blue is MSE error, and orange is our error, and you have the mean is the thick curve, and the shaded area, that's the variance. And what you see here is that A, with our content loss, the error increases more linearly from the starting time, and it also has a smaller variance, which both indicate that this issue we saw at the beginning, that yeah, after about 30 hours, the loss function doesn't give us any more information, is at least somewhat alleviated here. We still see that after a certain time, essentially the loss plateaus, but it at least seems to be improved with our content loss. Good. And with this, we can go to the real validation application, which was the super resolution. So again, the idea is we take a coarse image and do upsampling or downscaling, or want to increase the resolution, but in a meaningful way, so that we really respect the intrinsic structure of our data. And as I said before, as baseline, we used the recent work of Stengel et al., and we actually really used the GAN we put online, thankfully, so that we have a relatively fair comparison, which is really based on the SR GAN for natural images. Replaced in their implementation the mean squared error with our loss function. And the only difference we did, we restricted ourselves to 4x super resolution instead of, I think 20x was done in the original paper, which had more to do with training time and the availability of data than with anything else. Good. So, and let's look at some examples for the super resolution. In the middle, you obviously the ground truth. So we had the high resolution era 5 data. as baseline, and on the right you see the super resolution with mean squared error. That's the Stengel work. And on the left you always see our content loss, or the loss function derived from a neural network. And here I always highlight some regions where, I'm not sure how good the video compression of Zoom is. I assume a little bit that you don't see much difference, but I will put the slides online, and it will also be available over the KIT website, and maybe you can look after the talk then on at the details. So what you should see is that on the right with MSE, you hear the highlighted region, all the details are smoothed out. Whereas with our approach, you have a lot of the small fine-grained details that are also visible in the ground truth. And here's another example where you have the same effect, that MSE gives you overly smooth results where details are missing. And with our approach, you get much closer to the ground truth. Not exactly the same, but much closer. That's qualitative. If you want to have a quantitative comparison, that's the energy spectrum. So as a function of a wave number in the spherical harmonic domain, you look at the energy averaged over all time slices for the super resolution data. And this was also one of the benchmarks used by Stengel et al. Blue, that's the ground truth. So that's era 5 reanalysis. Green, that's MSE, and orange, that's our technique. And what you see here is that we get much closer to the true energy spectrum than with an MSE loss. So our content-based loss, our neural network-based loss function really improves here also the quantitative results. We get essentially upscaled fields that have statistics that are much closer to the ground truth. Similar, if you look at the semi-variogram, so at the spatial autocorrelation of both of velocity and dispulse are both for vorticity, you also see that, again, orange hours is much closer to a blue ground truth than with a mean squared error. So we can really, in the super resolution application, using a loss function that is derived from a neural network trained on our pretext task, predicting the time difference between slices, really gives us better results. Good. We can look. That's something that was not in the original paper. That's the total variation distance. Total variation measures essentially the norm of a gradient. That's something that is often used in computer vision, to especially for edge detection and to get good edge matches. And here we also see that the blue distribution, that's our work, is much closer to 0, which is on the very right, very intuitively, much closer to 0 than the orange distribution, which is with MSE. And the last thing I want to show is a little bit some results on local statistics. So we essentially looked at a single point, and we looked at the statistics if we did the super resolution over all different time slices we had. And we did this for 150 big cities, just as an example. The interesting thing here is we haven't actually really trained on statistics. This was something we tried out after we trained the network. There's nothing in the loss function also that tries to really give us good local statistics. And here's one example for Seattle. So in blue, the solid curve, that's the ground truth, again, era 5 reanalysis. In orange, which is a little bit behind the blue curve, that's our work, and in green, that's MSE. And you see here that for this location, at least we get substantially closer also in these local statistics to the ground truth. These results for the local statistics are a little bit mixed. So there are really cases where we are worse than MSE, and you see this here. We just list where we are better or worse if you just compute the error for the graphs for all the different cities. You see, in most cases we are actually better, but this is not entirely consistent. And you also see this if you look at really measure the distance in the sense of probability distributions with a Wasserstein distance. And you see that blue, that's our work here, it is overall, the distribution is closer to 0, so it's overall better, but you also see we have a higher variance in some sense than the MSE error. So there's clearly here still some work to be done, but you see there's at least some promise with our approach to also get good local statistics. Good. So summary of this part, it's possible, I think, to construct good or effective loss functions for atmospheric data with this approach of training a neural network on a pretext task. I also think this idea of predicting this time difference, that's actually something useful, not the least because this is something we can do for a lot of different input data. We often have this sequential data for reanalysis, for simulations, but also for satellite measurements. It's something that is widely applicable. And we also saw for super resolution that it really improves the results in an application. Local statistics is something we still should work on, but overall, it's very promising and it clearly improves some of the statistical results. With this, I want to give it a little bit an outlook of something one can look at in the future. Maybe that's also something we could talk about in the workshop. So if somebody is interested in any of these topics, maybe contact me. I will also be in California in 2 weeks. It's still stuck on this side of the ocean. Yeah, one thing we want to continue to do is the super resolution downscaling. We only looked at this 4x factor mainly for computational reasons, but yeah, we would really like to also go to 20x that was considered in Stengel et al. Work. And something I find very interesting is actually to adapt our approach, for example, also to local regions. Like we trained essentially with patches from all over the world and we got good results, but in a lot of applications, we are interested in a specific region. For example, like, yeah, you have in France or the United States or some part of the United States. And so one could think, for example, to take what we did now and train the neural network, but at the end of the training, then do a refinement stage where you only take local data so that the filters in the neural network maybe really adapt to the local behavior and the local statistics for a specific region on the globe. And you could also imagine doing something similar with just specific phenomena if you have suitable data for the training available. That's also fairly standard in machine learning these days, that you do some pre-training or some training with a big data set, and then at the end you only do refinement for a specific application. Something that I think is also very interesting is the detection of atmospheric patterns. So classic example would be extreme events, detect hurricanes, or if you have a big sequence of reanalysis or simulation, you want to automatically detect these events and classify them, and blocking and other events would be something similar. And yeah, where our work really came from, and where we maybe also want to continue, get back to eventually, is a hyperdynamic core for global circulation models, or where you have a core scale analytic simulation, but couple it to a neural network that does, for example, this kind of super resolution, GAN-based super resolution, to avoid the very immense costs you have if you go down to 10-kilometer resolution or something like this. Despite ultimately, we are only interested in fairly the core scale information. The talks yesterday talked a lot about these aspects. And something finally on the application side, really also consider maybe some application to addressing climate change. This is what Stengel et al., for example, did. But I think our work could also be useful in this respect. Something else, custom loss functions. Other atmospheric fields would certainly be interesting. I think it would also be very interesting. There are a lot of tracer particles. So you have some core dynamic variables, velocity vector field, temperature, pressure. But can you maybe decouple also in a neural network what you would classically decouple in a global simulation model in a GCM? More vertical layers would clearly be relevant and important. Then that's the idea essentially I already talked about, with transfer learning or refinement to local regions or to local phenomena. This would also be something I would be very interested to try out. And yeah, this point, we are often interested in global warming. We want to simulate, or we want to know, for example, how do extreme events evolve if under climate change. But with a neural network that is trained on data, how do we represent this distributional shift? There are some techniques in machine learning that in principle can deal with this. But yeah, this would be also one direction I would be very interested in exploring. How can we, for example, we really would like to have a parameterized model where you can feed in some parameters and we get a loss function that is still adapted to a setting, but that can also respect this distributional shift over time. Another insight for me also was that this and semi-supervised learning has, I think, significant potential for atmospheric data because we have very little label data. And yeah, this sidesteps the need for labeled data. And it's something that is used very generically for images today. And something I find that would be also very interesting would be to integrate heterogeneous data sources. So we only trained on real analysis, but what is if you combine real analysis with simulation, or for example, combine the high frequency, high resolution satellite data that is available today with like a much finer resolution, sub-meter resolution? How can you integrate it in our framework? And I think I should get to an end. Yeah, another point I think that is important, theoretical foundations, but I probably stop here, and I thank you for your attention, and I'm happy to answer any questions that are.
Yeah, thank you very much, Christian, for this really nice, say, technique. Potential a lot of applications. I suggest that there was in the chat, there was already some remarks and questions. So
yeah,
Andrew, do you want to ask a question?
Sure, I think maybe the comment says it better than I'll be able to say it verbally, but yeah, just wondering if you also considered kind of spatial pre-tasks. I think I've seen stuff both using spatial and temporal sort of pre-training tasks. So you could like predict the distance between two patches of space, and also sometimes predicting the exact value of time or space difference. It can be hard in certain contexts, and I'm wondering if you considered using a triplet loss, where you sort of penalize, you want to make sure that the distance between points that are nearby in space or time, or patches that are nearby in space and time, is smaller than the distance to something that's very far away or randomly selected.
Yeah, no, we didn't consider this. We started with a time which, yeah, it's clearly obviously combining with spatial temporal things makes a lot of sense. Also, if you think about what was done for images, right? You have static images, you want to add the time, but the spatial part is still relevant. No, we haven't done it, but it's more a question of time and resources to actually train the networks and experiment with these things. But I think it's very promising to also do this, yes.
If I may add to this.
Yeah.
Like recently in representation learning, there are also like these contrastive methods which are really popular, which basically predict is a sample similar or unsimilar to one another. And I think the triplet loss goes a bit in this direction. And personally, I would think this would be like an interesting direction to explore. And for me personally, the issue with these contrastive methods is a bit that they are a bit more complex from the architectural perspective. Like you have two networks, you have to train them in parallel, and you have to ensure that they don't collapse. And they're not that simple to train. So, but that would definitely be an interesting direction in my opinion.
Yeah, so this is Sebastian, my co-author, who did a lot of the legwork, and yeah, he is the one who is much more familiar with the details.
Yeah, thank you very much for the addition. Anyone else online has a question? I don't see anyone from the audience.
Yes, hi, Lorzana, great talk, thank you very much, pretty exciting. So I don't know if you have an answer or maybe just a comment. So did you start thinking about how could this be applied for regression problems rather than classification only?
Not in detail. I mean, we discussed some future work, and this was one of the things that came up, but we never got into the details. And Sebastian now also moved on to do his grad school somewhere else. But yeah, maybe we can discuss this in California in 2 weeks when I'm there. So we haven't really thought about this in detail.
Great, thanks.
Any other questions from the audience?
I'm Robert Pincus. I'm a domain scientist and more or less entirely ignorant of the machine learning, but I was curious if I understood you right. It seems like the insight is that you should measure the distance in the space of the neural net.
Yes, that's exactly the idea, that the neural net learns an internal feature representation that is tasks domain specific.
So the question would be why that, why you call it AtmosDist? Why is it specific to an atmospheric application as opposed to a general solution?
Yeah, so well, it's atmospheric, specific to atmospheric data because it's trained on the atmospheric data, and the network really learned the internal representation, we haven't looked at it. That's also something that's on my future work list. What I showed at the beginning, you really see that it learned features of natural images. And yeah, it's pretty slow here. So the network really is in this sense specific to at least the domain. Like for natural images, people have shown that you can train a neural network on natural image for a lot of different tasks. And these VGG networks that are used for the super resolution for the monkey picture, these are used for a lot of different things, but it has to remain the same task. And if you look at this network here trained for natural images, I don't think the cats and the dogs won't be very useful for atmospheric data. So,
well, the clouds sometimes have rabbits or so. No, I guess the point is that it's the trained network and not the method that you are stressing. Is that?
Yeah, so it's really the network internally learns features that are characteristic. So somehow how clouds or atmospheric dynamics evolve, this has to somehow be represented in the network, and that's important. And yeah, as the same way as it's important to, for example, have here the right ears, and it apparently distinguishes cats and dogs based on the ear shape. That's what one can take out of these images here.
So yeah, in theory, you could also use the pretext task for other spatial temporal data. I think there was also like a work where they just like tried to predict the order of spatial temporal data. So they had like a video, and they tried to predict, is this frame before the other frame or not? And I think our work is to some degree similar to this. So I guess it should also work for natural images as well. Yeah.
Yeah, but it's key to train the network on the data you're looking at least the domain. So that's also something very interesting, how far we can go with what we have to other applications. As I said, for natural images, these VGG networks have been used for, I think, hundreds of different applications, because we seem to have just some fairly generic features, but we don't know yet for our work.
Okay, thank you. Any other question?
Hi. Hi, Christian. This is Rose here. A very nice talk. So I'm just curious, like when you look at the representations of two twin networks, have you ever found any correlation between the learned representation and the non-stationary dynamics that you're looking at? Because I would imagine like the delta T you pick would affect the representation you learn. And if the underlying dynamic is highly non-stationary, then the representations will be very different.
Yes, I mean, we never looked at really stationary flows. We only trained on reanalysis, so this would be some validation experiment to maybe take more regular data or more chaotic data and see how the neural network, the internal representation changed. Yeah, for us it was really, we were happy to get it work on ERA 5. I'm a big fan of this data set because it contains a lot of things we cannot model, but we haven't looked into the network. What you see right now, right? You can visualize a little bit of what the network learns, and you can do various experiments to understand a little bit of the internal structure of what is learned. But we unfortunately didn't get to this yet, to see really, how are the nonlinear dynamics represented, how it deals with different scales, the scale interactions. All questions that would be very interesting to look at.
Okay, thanks.
Okay, any other one?
Yes, hi Christian. This is Antoine Blanchard.
Hi Antoine.
So my question, I think, is along the lines of Rose's question. And this is maybe a stupid one, but I'm wondering if, since you're working with physical fields, if there is a meaningful interpretation of the limit when delta t goes to 0. Specifically, does your architecture degenerate into like a singularity, or does it revert back to something that is maybe more trivial but better behaved, if that makes sense?
Yeah, I mean, we always at the moment we train on this whole, like we have 3 hours, 6 hours, up to 69 hours. I think we don't actually put in anything with delta t equals 0, Sebastian. No. Yeah,
we did actually like in the beginning. It worked as well. But for me personally, I think it's like kind of simple for the network to predict that the two images are the same. So for instance, it just has to take the difference and has to see, okay, it's 0. So I thought I'd maybe just leave it out.
Yeah, especially with the ResNet architecture.
So we don't have, and for training, we don't have. We don't have any samples for the training where the difference is 0. But we had in the beginning, actually, yes.
Yeah, okay, I see. All right, cool, thanks.
Yeah. Okay, one more question, maybe.
Hi, Christian. Thanks for the really interesting talk. I was curious if you've looked into applications in data assimilation. That's sort of one area in the atmospheric sciences where a lot of effort has been made on sort of, I guess, engineering loss functions.
Yeah, definitely, and all the analytic loss functions that exist, or a lot of them are motivated by data assimilation. No, we haven't looked at this application. It's also fairly far from my area of expertise. So if you have any knowledge or so, I'm happy to talk about how we can use our network maybe to try it out on this data set. Yeah, also like maybe for everybody, we are currently working on putting the code online. So it's already on GitHub. We just try to clean it up. And so there's an archive paper that is on the last slide. If you just go there, in the next few days, you will find the link to the code online. And if you want to try it out, you're also happy to just contact us and we can help you.
Great, thank you.
I have a final, maybe quick question.
Yeah, go ahead. Yeah.
So, I'm hoping that maybe we can discuss this in a few weeks. But since you're using a distance metric and also following a lot of the other questions here, have you tried experimenting with different distance metrics? And especially, I'm thinking about with distance metrics, you can start exploring that underlying manifold of the data, which, you know, you're using a semi-supervised, sort of unsupervised way of going at this. So I would think that using different distance metrics, especially in terms of learning more about the local or the global information, and of course also tailoring this to your application, could be beneficial. But I might be misunderstanding how you're using and defining the distance metric, because I'm not sure I caught that from the slides.
Yeah, I mean, I think one thing one could do with our distance metric is to essentially think about studying the manifold that is represented through it, that is defined implicitly, at least locally, through the kind of Riemannian metric we have. I mean, you also would have to look at actually at the properties. So this would be one direction. I think you're asking a little bit the inverse way, how you can use the manifold structure to still improve the metric. So yeah, what we did at the moment, we took the L2 norm of the last layer of a neural network, which is the most simple thing you can think of. So there are a lot of ways to be more careful about what you do about the neural network, and so that's also something we still have to do.
Yeah, cool. Thanks for the talk.
A lot to do. So thank you very much, Christian, and also Gus for the nice talks. Everybody else for the really good discussion and questions. And we have a half an hour break now where you can drink coffee nicely, probably in the sun, and we go having a little dinner in the dark. So see you back at 11 o'clock California time.